Depending on the resource you're using, either a textbook, handbook, or an instructional website, or even an engineer that works with gears, you'll find a different categorization for the available types of gears. We will end up using a 4-main category system with spur, helical, bevel, and worm gears, but we'll talk about those later. Today, we will look at the simple spur gears to identify some of the vocabulary and nomenclature we will use for their geometry, so that we can cover the kinematic relationships, force, torque, and power transmission, and eventually stresses and strengths that will allow us to calculate the overall reliability of gear systems. And of course, gear systems is not just the analysis of the gears themselves. This will include the shafts we studied in earlier videos, as the different gear types introduce all the external forces that affect the shaft design we covered, and all of the fatigue concepts we've been applying to the different machinery components. After this, we will transition to bearings, which of course is related to the shafts, and that includes bearings design and selection. We've talked about pitch for other components, like screws and springs, and in every case, the pitch refers to a distance between repeating elements, like threads in the case of screws, or coils in the case of springs. If we look at a couple of teeth of a spur gear, where would you define the pitch, or the distance between one tooth and the next? Would it be at the base or at the top? Would it be a straight line distance, or over the circumference of a circle? It makes sense that it is defined as an arc, a curved distance along the circumference of a circle, but where would that circle be located? We define circular pitch as the arc distance from one tooth to the next, which means is not the distance on a straight line, but a distance along the circumference of a circle, in this case, along the pitch circle. The pitch circle is what separates the dedendum from the addendum. When one tooth of a spur gear is in contact with the tooth of another gear, the point of contact will slightly shift as both of them are rotating. The average location of the point of contact occurs exactly at the pitch circle. Alternatively, you could just picture that the pitch circle of one gear will intersect with the pitch circle of the maiden gear. This pitch circle has a diameter that we will call the pitch diameter. Remember when you talked about the radius of a gear when working on simple angular velocity and torque topics in physics? Or the radius of a gear in a simple gear setup during your mechanics of materials torsion examples? What radius were you using then? Was it the distance from the center to the base of the gear? From the center to the top of the teeth? Even if you didn't know it then, it was a radius equivalent to the pitch diameter divided by 2, or just the pitch radius. So every time we refer to the diameter of a gear to talk about the relationship between number of teeth, angular velocity, or torque, we will be using this pitch diameter. The circular pitch, that distance between one tooth and the next, will for this reason be equal to the circumference divided by the number of teeth. Even though the circular pitch is what defines that distance, which makes total sense for a pitch, we usually use the module for metric units, which is the same as the circular pitch without the pi, and the diametral pitch for English units, which for whatever reason is the reciprocal of that. The units of the module would be millimeter per teeth, and the units of the diametral pitch are teeth per inch. The involute profile refers to this very precise shape the tooth has. This shape would guarantee that the point of contact between two teeth, one from each gear of gears in contact, occurs where the two surfaces are tangent to each other. The reason I say would guarantee instead of stating it as a fact is that this only happens for perfectly formed, perfectly smooth, and infinitely rigid teeth, which of course is not the case. Regardless of the imprecisions, the fact that the point of contact occurs where the two surfaces are tangent to each other means that the forces at any moment during contact are pointing in one and only one direction. This line is known as the line of action, and what's important about it is that the angle between it and the tangent line to where the pitch circles meet is called the pressure angle phi. This angle, which used to be 14.5 degrees and is more commonly 20 degrees now, but can take other values, will be very important when we talk about forces and force components, one of which will transfer the torque from one gear to the other, and one of which will cause that bending moment on the shaft that we mentioned before. But more about that in a later video. Now, we're gonna develop 3 separate relationships from 3 distinct conceptual bases. When the gears are designed and mated so that they produce a constant angular velocity during service, which means neither of them will stutter or stop while the other one is still rotating, we say the gears have conjugate action. For the gears to mate properly, the circular pitch, that distance between one tooth and the next, has to be the same for both gears, otherwise that teeth distance would not match. Knowing that the module, diametral pitch, and circular pitch are all equivalent, let's use the diametral pitch to say that P1 has to be equal to P2 for proper mating. If this is true, then the ratio between number of teeth has to be equal to the ratio between the diameter of the gears. And remember that we will always use the pitch diameter as the standard diameter for gears. The second relationship comes from the fact that you don't want the gears to slip. Slipping would introduce friction, which would not only cause the gears to deteriorate over time, but it would mean that the efficiency of the transmitted torque is drastically reduced. Without gears slipping, we have that the arcs from each gear after a specific amount of time are the same, which means that the linear velocity at the pitch circle is the same. From basic physics, we know that the linear velocity is equal to the angular velocity times the radius, and therefore the radii ratio has to be the reciprocal of the angular velocity ratio. Since we usually use the diameter and not the radius, and since we usually talk about revolutions per minute instead of angular velocity, we can multiply by 2 on the numerator and denominator of the left-hand side and divide by 2 pi on the numerator and denominator of the right-hand side. The left hand would be the ratio between gear diameters, and the right-hand side would be the number of revolutions per minute, since there are 2 pi radians per revolution to find omega, the angular velocity. Finally, if we assume that there is no power loss when transmitting torque from one gear to the next, and we'll fix this in a minute with the efficiency concept, then the power in gear 1 is equal to the power of gear 2. Again, from basic physics, power is angular velocity times torque. Dividing by 2 pi and multiplying by 60 on both sides, and I do include the 60 now because power in watts would necessitate an angular velocity in radians per second, not minute, we get RPM times torque, which results in a relation between revs per minute and torques. If we put all of these together, we find that with only one of the ratios, we can find the other three. If there is a loss in power, we introduce the efficiency eta into the last relationship, a fraction between 0 and 1, but we'll talk more about that later. In a 4-gear system that transmits power from shaft A to shaft C without any losses, gear 2 has 40 teeth, gears 3 and 5 are the same gear with 10 teeth and a module of 0.5 millimeters per tooth, and gear 4 has a pitch diameter of 15 millimeters. If shaft A is rotating at 200 revs per minute, what is the input and output torque and the output revs per minute if the power going in is 50 kilowatts? The first one of these questions is almost not related to what we learned today. Maybe it's related to what we reviewed today from physics. If power is equal to the torque times the angular velocity, and the angular velocity is 2 pi over 60 times the revolutions per minute, then the torque is equal to power times 60 over 2 pi n. With 50,000 watts and 200 revolutions per minute, the torque would be 2.39 kilonewton meter. To find the revolutions per minute of shaft C, which is the same as the revolutions per minute of gear 5, I'm gonna need to know the revolutions per minute of gear 4, 3, and 2, and use the relationships we came up with today. I know gear 2 rotates at the same angular velocity as shaft A, and since I know the number of teeth of gear 2 and gear 3, I can use the relationship between revs per minute and number of teeth to find that gear 3 rotates at 800 revs per minute. Gear 3 and gear 4 are on the same shaft, shaft B, and therefore rotating at the same speed. To find the revs per minute of gear 5, I either need the relationship between the number of teeth or the pitch diameter between gears 5 and 4. And since I have the module of gear 5, which is the relationship between the number of teeth and the pitch diameter, I can find that the pitch diameter of gear 5 is 5 millimeters. Since I now have the diameters of gears 4 and 5, I would use the relationship between diameters and revs per minute for gears 4 and 5. From this, I find that the revs per minute of gear 5 is 2400 RPM, which is the same speed as the rotation of shaft C. Finally, to calculate the output torque, I could either repeat this procedure I just did and use relationships that allow me to calculate the torque instead of the revs per minute, or I can use the given power and the revs per minute I found for shaft C to find that torque. If the problem didn't ask for the output speed, but it did ask for the output torque only, I would probably use the relationships from today, instead of using those to calculate a speed that wasn't part of the questions, to then calculate the torque with the power and that speed. As you can see from this gear system, the torque coming in is 12 times the torque coming out, but the output speed is also 12 times higher than the speed I'm giving the system. There are many reasons where you would want to gain velocity even though you lose torque, like for example the higher gears in the transmission of your car, but also you can lose some speed to gain torque, like for example the power screws we studied before. If you want to check out other problems where we make use of these relationships we derived today, make sure to check out the links below. In the next video, we'll take a look at gear trains, somewhat related to what we did today with the example, and a specific case of that, the planetary gears, which will allow us to understand the rotation of the gears and the direction of that rotation. Thanks for watching. A 17-tooth spur pinion has a diametral pitch of 8 teeth per inch, runs at 1120 revolutions per minute, and drives a gear at a speed of 544 revolutions per minute. Find the number of teeth on the gear and the theoretical center-to-center distance. This is the first example for the Gears Basics and Relations main video. Link to that video is in the description below. I'll mention this in a future main video, but the convention for gears is to label the first gear as gear 2 and add 1 for each new gear, reserving the 1 sub-index for the device that is driving the system. The name pinion is the name we give a gear that is driving another gear. So in this case, gear 2 is the spur pinion. The center-to-center distance is important because this is potentially the distance between the shafts that are carrying the gears. From that main video, we know that the ratio between the number of teeth is inversely proportional to the ratio between the rotational speed. The number of teeth on the gear is therefore 35. The theoretical center-to-center distance will be the radius of gear 2 plus the radius of gear 3, which is their pitch diameters over 2. The pitch diameter for the pinion, or gear 2, will be the number of teeth over its diametral pitch. And since the ratio between the pitch diameters is directly proportional to the number of teeth, the pitch diameter of the gear, or gear 3, is equal to 4.375 inches. Substituting these values, we find that the theoretical center-to-center distance is 3.25 inches. For more examples on gear basics, make sure to check out the links in the description below. Thanks for watching. The double reduction helical gear set is driven through shaft A through an engine that has a power of 2.2 horsepower. With a torque of 38.5 pound-inches. What are the input and output revolutions per minute, and therefore the velocity ratio? This is the second example for the Gear Basics and Relations main video. Link to the first example and that video are in the description below. Notice that the velocity ratio, which is the output velocity over the input velocity, or RPMs, could be calculated from the information about the number of teeth and the diameters of the gears. We wouldn't need the information about the torque and the power. However, since we also want to know what the input and output speeds are, we'll find those first and use their values to calculate the velocity ratio. We'll label the gears just as I explained during example 1. The rotational velocity of shaft C will be equal to that of gear 5. The ratio between the speeds of gear 5 and 4 are inversely proportional to their diameters, which means we have the speed of gear 5 as a function of the speed of gear 4. Gears 3 and 4 rotate with shaft B, so their speeds are the same. The ratio between the speeds of gear 3 and 2 are also inversely proportional to their number of teeth, which means we have the speed of gear 3 as a function of the speed of gear 2. The speed of gear 2 is the same speed of the shaft A, which is receiving 2.2 horsepower and 38.5 pound-inches of torque. Since 1 horsepower is 550 feet-pound per second and there's 12 inches in a foot, the horsepower that shaft A is receiving is 14,520 pound-inch per second. Since power is equal to the torque times the angular velocity omega, The angular velocity of shaft A is 377 radians per second. For every 2 pi radians, there's 1 revolution and 60 seconds for every minute, and therefore the rotational speed of shaft A is 3600 revs per minute. This means that gear 3 is rotating at 10,800 revs per minute, and that gear 5, and therefore shaft C, is rotating at 54,000 revs per minute. Using these values, we find that the velocity ratio is 15. This velocity ratio tells us how many times faster the output rotational speed is with respect to the input rotational speed. For one more example on gear basics and relations, make sure to check out the link in the description below. Thanks for watching. If the press head of the press shown can move at 7 inches per minute with a motor that has 0.25 horsepower and lead screws with a 1/4 inch of pitch, what is the speed of the motor and what is the mechanical advantage of the system? This is the third example for the Gears Basics and Relations main video. Links to that main video and the 2 previous examples are in the description below. As usual, we'll begin by labeling the gears. And notice that both gears for each lead screw are labeled as gear 5, since they need to rotate at the same speed and deliver the same amount of torque. The speed of the motor will share the speed with gear 2, since they are located on the same shaft. The speed ratios are inversely proportional to the diameter ratios, and this is true for both sets of gears, gears 2 and 3 and gears 4 and 5. Since gears 5 are rotating with their lead screws, and we know that the press head, which is the nut around those lead screws, is moving at 7 inches per minute, we know that gear 5 is rotating at 28 revolutions per minute. Gear 4 is therefore rotating at 224 RPM, as is gear 3, which is located on the same shaft. With this information, we see that gear 2 is 1,792 RPMs, which is also the speed of the motor. For a gear system, the mechanical advantage is defined as the output torque over the input torque. In the next main video, we'll learn about the train value and how both the velocity factor and the mechanical advantage can be found with the relations between the gears. However, for this video, let's calculate the torque that the motor is exerting on the system and the output torque at the screw. With 0.25 horsepower in pound-inch per second, and with the rotational speeds as angular velocities in radians per second, we divide power by angular velocity to find the torques. Notice that the output torque for each screw will have the power cut in half, since the power is split into 2 power screws. Since the output torque is 2 torque values of 281.5, the mechanical advantage is 64. Thanks for watching. You might have noticed from the example we covered during the last main video that we labeled our gears starting with a 2. Since the first driving gear is not moving on its own, but most probably due to it being located on a rotating shaft, we usually set aside the number 1 for that first element of rotation. From the relationships we derived then, we know that if we know the number of teeth of 2 mating gears, the diameters of 2 mating gears, or one of the diameters, the number of teeth of the other, and the diametral pitch or module, we can find the ratio between their rotating speeds. Even though the term gear trains technically refers to any gear system that has 2 or more gears, therefore making every gear system a gear train, we commonly use it to talk about a system where there are 3 or more gears on the same plane. Regardless of the number of gears, any system that is connected to transmit power from one end to the other will have elements that are driving and elements that are being driven. And notice that I'm using the word elements since you can even have pulleys, for example, besides just gears. For a 5-gear train consisting of 3 gears in the same plane, 2, 3, and 4, and obviously the other 2 on another plane, we can find out the speed of gear 6 if we know the speed of gear 2, and of course the number of teeth or the diameters of the gears. From what we know, the speed of gear 3 would be N2 over N3 times the speed of gear 2, and 4 would be N3 over N4 times the speed of gear 3, which we already have in terms of N2. We know that N4 and N5 rotate at the same speed since they're probably on the same shaft, and the speed of gear 6 would be N5 over N6 times the speed of gear 5, which we also have in terms of the speed of gear 4. This expression shows us several things. The first thing is that N3 appears both in the numerator and the denominator, and that's totally fine. Of course, this means that mathematically it'll cancel out, which means that physically it's not affecting the output speed of the system. These gears are called idler gears, and they are usually used just to change the direction of the rotation, or in other words, keep the direction of the rotation of the two gear ratios you actually want to use. In this case, have gear 2 and 4 modify the speeds and torques, but have both of them rotating in the same direction. If we didn't have the idler gear, gear 3, gears 2 and 4 would have an opposite direction of rotation, instead of having them both rotate clockwise like in this example. The second thing is that the gears that I have in the numerator are those that are driving other gears. The gears that I have in the denominator are those that are being driven. The train value, E, is defined exactly as that fraction. A fraction with the number of teeth of driving gears on top and the number of teeth of the driven gears in the bottom. Now, you don't need to memorize which ones go on top and which ones go in the bottom, or even remember the name of the train value. If you're trying to find the speed of 2 in terms of the speed of 6, and suppose for a second that we didn't have any other gears besides those two, you know that from our first and very simple relationship, N2 is N6 times N6 over N2. This means that the number of teeth always goes together with the speed of the gear you are multiplying it by. If the other gears do exist, the expression would still be speed of 6 times N6, and by identifying that 6 is a gear that's being driven, you add all of the number of teeth of the driven gears next to N6. Then at the bottom, you put the rest of the gears, in this case the driving gears. Notice that the two expressions are correct, and that I'm not using a memorized expression for the train value. I'm only using the simple relationship we derived during the last main video. The third thing we can notice here is that if we evaluate the speed of gear 6 with a given speed of gear 2, the numerical result would have the same sign as gear 2. Mathematically, that would happen because the number of teeth of every gear is a positive value. So if N2 is positive, N6 is positive, and if N2 is negative, N6 is negative, which in this case means that gear 6 would be rotating clockwise, and that's not true. With a quick analysis of the rotation direction of each gear, we can see that if gear 2 is rotating clockwise, gear 6 would be rotating counterclockwise. For this reason, for any gear system, the best way to find the rotation direction is to do a separate analysis instead of remembering rules about the train value expression. In this case, since I know the direction of rotation of gear 6 is opposite to that of gear 2, I would just add a negative sign to the train value. Worth mentioning now is the rotation direction relationship between different elements. Mating spur gears will have opposite direction of rotation, as will mating helical gears. Notice that the top views show the rotation direction of the gears as a vector that represents the rotation on the surface closer to the viewer. For bevel gears, you would always see direction vectors either coming in or coming out of the intersection point, since teeth in contact would be moving in the same direction. For worm gears or helical gears that are crossed so that their axes are perpendicular to each other, the trick is to follow one helical tooth through its motion. If the visible face of the top gear is moving down, this yellow tooth will be moving down as well. After an instant, the tooth will have moved down a little, which means that the tooth from the bottom gear that was in contact with the tooth from the top gear will have moved left, and therefore the bottom gear would have moved counterclockwise. This analysis can be done for any configuration. If the gear on top is moving up, the tooth from the top gear would be moving up with it, and therefore the tooth from the bottom gear would be moving to the right. We'll talk more about helical and worm gears later, but for now, note that a slight clockwise rotation of the orientation of the teeth of a spur gear is called a right-hand helical gear, and a slight counterclockwise rotation of the orientation of the teeth is called a left-hand helical gear. Same goes for worm gears. And finally, since pulleys are often used in speed-torque transmission systems, just know that connected rotating pulleys will have the same direction of rotation, which is pretty obvious if you follow any moving location on the belt, cable, or chain. Going back to the gear trains, when some gear axes are allowed to rotate about others, which physically means that the shafts that hold the gears are rotating about other gears, we call these trains planetary. Planetary trains always include a sun gear, an arm or a planet carrier, and one or more planet gears. The relative angular velocities of a gear with respect to the arm, which is the same to say the relative RPM, are given by the typical relative speed definition, which is the subtraction between the RPMs of the gear and the arm. For example, N23 is N2 minus N3. We could do the same for the speed of gear 5 relative to the motion of the arm. N53, which means the speed of 5 with respect to 3, the arm, is equal to N5 minus N3. And by dividing the equations, we see that N23 over N53, which is just N2 over N5, since their point of reference, in this case the arm 3, is the same. What would N2 over N5 be? For any gear train, taking into account what we learned today, it would be exactly the reciprocal of the train value E. In general, the train value for a planetary gear system will be the speed of the last gear, in this case gear 5, minus the speed of the arm, in this case element 3, over the speed of the first gear minus the speed of the arm. Let's work on two simple examples today. We'll start with what we just talked about. In this planetary train, the sun gear is rotating clockwise at 100 RPM, and the ring gear, which is just a ring with teeth in the inner part, is rotating counterclockwise at 10 RPM. What is the speed and rotation direction of the arm and gear 4? From what we just learned, we know that the speed of the arm, the last gear, the first gear, and the train value are related. And we know that the train value is given by the number of teeth of the driving gears, in this case 2 and 4, since 2 is driving 4 and 4 is driving 5, divided by the number of teeth of the gears that are being driven, in this case 4 driven by 2 and 5 driven by 4. Additionally, we know that this train value needs to be negative, since the rotation of the gear 2 is in opposite direction of the rotation of gear 5. A brief clarification here. Even if the given speed of 5 was clockwise, gear 5 will always rotate counterclockwise with respect to gear 2. Since the yellow line of gear 2 is clockwise and the yellow line of gear 5 is counterclockwise and therefore opposite in direction, that negative sign needs to be there for the train value always. It might happen that because arm 3 is moving clockwise, despite 4 moving counterclockwise, ring 5 might also be moving clockwise, which is a simple dynamics problem. But again, 5 with respect to 2, following the yellow lines, will always be opposite in direction of 2. Substituting the given values and solving for N3, which is the speed of the arm, would give me an arm speed of 12 RPM in the clockwise direction. Knowing the speed of the arm, I can find the relative speed of gear 4 with respect to the arm, and also the speed of gear 2 with respect to that same arm. The ratio between speeds 4 and 2 with respect to the arm is just the ratio between their speeds, which again, due to that basic relationship between number of teeth and speed, is a value I know. Solving for N4 from this equation, and knowing once again that the direction of rotation of gears 2 and 4 are opposite, and therefore a negative sign needs to be added, we find that the speed of gear 4 is 46.6 in the counterclockwise direction. Now let's work on another problem. The train shown is driving gear 9, knowing that the rotation of shaft A is 600 RPMs. What is the output speed and the direction of rotation of gear 9? Let's start by answering the direction of rotation question. If gear 2 is rotating as shown in the figure, we know that the front face of the gear 2 that we're seeing is moving up, and therefore 3 is moving down. With it, since it's on the same shaft, 4 is moving down as well. 5 will be moving left, since both teeth at the intersection are moving into the screen. The belt on the pulley 6 will be moving left, and with it, pulley 7. The worm gear 8 will be moving with the pulley, which means that the teeth on the right side of the figure we're seeing will be moving down, and so would the teeth of gear 9. To find the speed value of gear 9 as a function of the speed of gear 2, and by remembering what I said at the beginning of the video, that lowercase 2 will go together with capital N2, I identified that gear 2 is a driving gear, and so is 4, 6, and 8. The gears being driven would be 3, 5, 7, and 9. Since elements 6 and 7 are not really gears, I would not be able to use information about their number of teeth. However, since the ratio of number of teeth is the same as the ratio between the diameters, which is the first relationship we learned, I can rewrite the expression in terms of diameters for 6 and 7 to find that the speed of gear 9 is 3.75 RPMs, and that in the counterclockwise direction. If you want to check out other problems related to gear trains and planetary trains, make sure to check out the links in the description below. In the next video, we will start looking at the interaction forces between the different types of gears, including how to calculate their components and what each one of them does to the system. Thanks for watching. Shaft A is rotating at 600 revolutions per minute in the direction shown. What is the speed and direction of rotation of shaft D, and what are the input and output torques if shaft A is fed with 1000 watts and the system has 100% efficiency? This is the first example for the Gear Trains and Planetary Gears main video, link below. To find the speed of shaft D, which is the same as the speed of gear 7, we'll use the relationship between number of teeth and rotational speed. This relationship shows us that the ratio between the speeds is inversely proportional to the number of teeth. And from what we learned from the main video, and since we can identify that gear 2 is a driver gear, we'll add the number of teeth of all the other driver gears to the numerator of this fraction. 2 is driving 3, 4 is driving 5, and 6 is driving 7. The denominator will have the number of teeth of the gears that are being driven, just like gear 7. 3 is being driven by 2, 5 is being driven by 4, and 7 is being driven by 6. This fraction is what we refer to as the train value E. The speed of gear 7 and therefore shaft D would therefore be equal to 47.06 revolutions per minute. To answer the direction question, we see that the front face of gear 2 is going upward, gear 3 is therefore going downward, as is gear 4 since they're on the same shaft B, and because of the helix angle of the helical gear 4, gear 5 would be rotating counterclockwise, and with it gear 6, and therefore gear 7 and shaft D would be rotating clockwise. To address the torque question, we know that power is equal to torque times the angular velocity in radians per second. And since we're assuming that the system is 100% efficient, we can find the torque by using the same power value at the input and at the output. The angular velocity can be found if we multiply by 2 pi radians for every revolution and dividing by 60 seconds for every minute. The input torque would be equal to 15.9 Newton meters, and the output torque would be equal to 202.9 Newton meters. Notice that the mechanical advantage is the reciprocal of the train value for systems with 100% efficiency. For another example on gear trains, make sure to check out the link in the description below. Thanks for watching. For the gear train shown, what is the speed and the rotation direction of shaft C, and what is the distance between shafts A and B if shaft A is rotating at 540 revolutions per minute? This is the second example for the Gear Trains and Planetary Gears main video. Links to the first example and that main video are in the description below. We'll start with the direction of the rotation of shaft C. The front face of gear 2 is moving down, and therefore the front face of gear 3 is moving up. Gear 4 is on shaft B with gear 3 and is therefore also moving up. The teeth that are in contact from gear 4 and gear 5 will be coming out of the screen, meaning that the front face of gear 5 is rotating towards the left. Shaft C is rotating with gear 5, which means that gear C is rotating clockwise when seen from the top. The speed of shaft C is the same as the speed of gear 5. The speed of shaft A is the same as the speed of gear 2. With the rotation speed to number of teeth relationship, we see that gear 2 is a driving gear, as is gear 4. We also see that gear 5 is being driven just as gear 3 is. Gear 5 is therefore rotating at 162 revolutions per minute. For the distance x between shaft A and shaft B, we need the pitch radius of gear 2 and gear 3 or their pitch diameter. If their diametral pitch is 8 teeth per inch, and from the units we see that the diametral pitch is the number of teeth divided by the diameter in inches, we get that the diameter of gear 2 is 1.5 inches, and since the diametral pitch of gear 3 is the same for them to be compatible, the diameter of gear 3 is 5 inches. The distance between shafts is therefore 3.25 inches. For one more example on planetary gears, make sure to check out the link in the description below. Thanks for watching. In the reverted planetary train illustrated, what is the speed and direction of rotation of the arm if gear 2 is unable to rotate and gear 6 is driven at 12 revolutions per minute in the clockwise direction as viewed from the bottom of the figure? This is the third example for the gear trains in planetary gears main video. The links to the previous examples and the main video are in the description below. From that main video, we know that the train value E will be equal to the speed of the last gear minus the arm gear over the first gear minus the arm gear. But the train value E doesn't need to be defined anyways. This fraction on the right is just equal to the speed of the last gear over the speed of the first gear with respect to the arm. And since they're both with respect to the same frame of reference, in this case the arm, that ratio is the same as the speed of the last gear over the speed of the first gear. Additionally, we can define the last and the first gear however we please. If we say that the first gear is gear 2, the last gear would be gear 6. Since the ratio between the speeds is inversely proportional to the number of teeth, and we identify that gear 2 is a driver gear driving gear 4 just like gear 5 is driving gear 6, and 6 is being driven by 5 just like 4 is being driven by 2, we find an expression to solve for the speed of the arm gear. The only value we're missing from this expression is the number of teeth of gear 6. But since we know that the distance between the shafts can be defined in terms of the diameters of gears 2 and 4, or in terms of the diameters of gears 6 and 5, and we know that the diameters are directly proportional to the number of teeth, we find that gear 6 has 34 teeth. Using these values, we solve for the speed of the arm, and either with the mathematical sign or a quick direction analysis, we see that the arm gear, or gear 3, is rotating clockwise as viewed from the bottom of the figure. Thanks for watching.